Hello again. Welcome back. Got a topic here today that we're going to talk about, which has to do with inductors and capacitors in our AC circuits. And what it's going to do for us is it's going to help break down the time it takes to fully charge a capacitor, your cell phone battery, your electric vehicle, your computer laptop. Did you ever notice you throw that phone onto the charger at night after dinner, and you were at like 20%, and it really went from 20% to like 67%, no problem, like really quick. You finished taking the garbage out, came back in the house, and oh, the phone was at 25%. Now it's at 67%. And then you sit there and you watch a show on Netflix or whatever, and you go and you look at your phone, and it went from that 65% to say 85%. You're like, wait a minute, that show is 45 minutes long. What happened here? Really fast from 25% to 60%. But now, it got above 60%, and it's taking a lot longer for my phone to fully charge. That's the time constants. That's the amount of time it takes to get fully charged battery, fully developed magnetic field in an inductor, and we can break them down. We do this a lot for electric vehicle charging. And now you're seeing that you have class 1, 2, 3 electric vehicle chargers at 150 kilowatts, 250 kilowatts, 350 kilowatts. And why is this one faster and that one's slower? So, and every time I sit there, it takes a little bit more. It's the time constants for that battery. And each one of the capacitors and inductors are broken down into 5 time constants. 5 time constants. And we have formulas to give us the amount of time each one of those 5 time constants is going to take. And we look at the one for inductance. We have the amount of time equals L, which is inductance, measured in henries, right? Divided by the internal resistance of that device, the wire that coil is made of. So we take the henries divided by the internal resistance, we get one of these 5 time constants. 1 of 5. So if we wanted to know how long it's going to take to fully charge our battery, we can take that result of our 1 time constant and multiply it by 5. So if we have 2.25 seconds for 1, we multiply that by 5, and we get 1.25 seconds. That's how long it would take to fully charge that particular capacitor, build that magnetic field in that particular inductor. And here on the left-hand side, we see this exponential curve, meaning it doesn't end. There's always something left. Exponential. And it really breaks down into why the 5 time constants are there and what each one of them means, right? And this is why we see that big jump when we first connect our battery to a voltage source, or hook our cell phone up to the receptacle. We see that jump right up to that first time constant is 63.2% of the 100 that we're looking for. It's a real big jump. So hopefully that starts to bring that into picture. Then we can figure out what percentage will we be after the next time constant. Because we'll take what's left after 63.2% to get to 100. It's 36.8%. I got 36.8% left. And what I'm going to do is I'm going to take 63.2% of this 36% to figure out where I'll be after 2 time constants. How much closer am I to 100? If we multiply 36.8% by 0.632, because again, the 36% is the whole, we find out that we get a value of 23.25. We take our 23.25, we add it to 63.2%, and we get 86.4%. A lot closer to that 100 mark. But now you can start to see why it takes a lot longer to get to fully charged here, because there's not 36.8% left anymore. There's not. What we have left to get to 100, 13.6%, right? Or 13.6% would get us to 100 and we would be done, but it doesn't work that way, does it? We have to multiply that by 0.632, and then we get up to 94.9%, and so on and so forth. Real fun tidbit here, especially for the apprentices I have in the room. We can always remember the percentage of the time constant because it's IBW 236 backwards. So that's a little feather in the cap my apprentices get to use. You go, oh yeah, I remember what that time constant percentage is. It's 236 backwards, 63.2%. Hopefully you find this video helpful, and let us know if there's anything. We'd love to hear from your feedback. Appreciate your time, and I hope you have a wonderful day.